Good morning and welcome to Friday of week 4 of your Physics 5 a day, and we're finishing off Astro here today. We finished up yesterday thinking about the brightness of stars as they appear to us from our viewpoint here on Earth. And what we mean by that is the light that's arriving at Earth from these stars, what's the intensity of that light? And we saw that it depends on the total power the star is radiating out in all directions, and the surface area of the sphere, where r is the distance from the star to us. Now, we have a special name for the power of a star, and that's luminosity. So luminosity is the total power radiated by a star. And it's just measured in watts as usual. So when you see L for luminosity, just think power of the star, the total power radiated. And it turns out that the total power radiated per unit surface area of a black body is directly proportional to the fourth power of its temperature. Now remember that stars are quite a good approximation of a black body, so this, which is called Stefan's law, applies to stars. We can use it on stars. Now, replacing the direct proportionality sign with a constant, that constant is called Stefan's constant, and that's its value. It is on your formula sheet. Now, what's fun about this is that if you know the luminosity of a star and you know its surface temperature, which we saw how to do that yesterday, then you can work out how big the star is. You can work out the radius of the star. And this formula, the Stefan's law formula, it often appears in questions with Wien's displacement law, because you've got temperature in both of those. So you often use one to find the temperature, then put it into the other one and work something else out. And so putting all those three formulae together, have a go at the first question today. And it's the displacement law up first there, leaving you to substitute the numbers. Remember to put your unrounded value because it's a show that question. Now, a bit tricky perhaps this next bit, but look at the units to help you. So here we've got the radiation from the sun arriving at the top of our atmosphere, and look at the units here, kilowatts per metre squared. Power, that's a power per unit area, so this is an intensity. And as usual, we're imagining the power being spread out over the surface of a sphere. There's the star at the centre of the sphere, and here's us out on the surface of the sphere. And so, rearranging the intensity formula there, we get the power of the star, which is, of course, the luminosity. So that's our value for the luminosity there. And finally, I haven't left enough space to do this really, so you're going to have to do the substituting yourself. But this is the luminosity of the star that we've just worked out. That's the temperature. Use your unrounded value from this question. And remember that this r now is the radius of the star. So this is surface temperature and radius of the star, as opposed to that r, which was how far are we from the star.